Hello, welcome back. We are on the penultimate chapter of materials kinetics, chapter 25, chemical reaction kinetics. Now, if you were taking a chemical engineering course on kinetics, probably most of the course would be devoted to this topic of chemical reaction kinetics. Since this is a material science and engineering course, we focused on many other areas, and we're going to devote just this one lecture to give an introduction to the basics of chemical reaction kinetics. The outline for today is that we're going to cover the rate of reaction, order of reactions, equilibrium constants, first order and higher order reactions, reactions in series. Then we're going to get to the temperature dependence of the reaction rate and obtain the Arrhenius formula using a different method compared to what we had before. Then we will cover heterogeneous reactions and solid-state transformation kinetics. So let's dive into it. Now, when we consider the field of reaction kinetics, we're going to consider three different types of reactions: homogeneous, heterogeneous, and solid-state reactions. Homogeneous reactions in chemical engineering generally occur in fluids, where the reactants and the products exist in the same phase. In contrast, for heterogeneous reactions, the reactants and the products exist in different phases, or perhaps the reaction occurs at some interface. So if they're in the same phase, it's homogeneous, and if they're in different phases or at an interface, that would be a heterogeneous reaction. Finally, solid-state reactions are, of course, in which the reactants and the products are in the solid state. So let's consider kind of a generic chemical reaction here, where you've got some quantity of A and some quantity of B, and they react to form these reactants C and D. The species are given by the capital letters here, and the amounts of the species are given by the small letters. So small a amount of capital A, for example. Now, the number of moles of this capital C at any time after the reaction has begun can be denoted as this N sub C. So the little n here is the number of moles, and the subscript is the species. So this is the number of moles of C. And we can express this with the following equation here. So the N sub C is equal to the N naught sub C. This is the initial amount of that species C. Plus then our stoichiometric coefficient here, this little c, times our parameter Kc, which is the extent of the reaction. So this parameter Kc is telling us how much of the additional quantity of C that we're getting as a result of this reaction. This tells us how far along the reaction has progressed, and therefore it is known as the extent of the reaction. Now, with these stoichiometric coefficients here, the general form for the extent of the reactions is equal to, so 0 is equal to, and then the summation of all of our stoichiometric coefficients, nu sub I, for all of the various species here, I, times A sub I, so whatever that species happens to be. Now with the stoichiometric coefficients, the little n sub I, the mole fraction of species I, is equal to the initial mole fraction plus then the stoichiometric coefficient times the extent of reaction Kc. Now, these stoichiometric coefficients are going to be positive for products because we are producing products. So the concentrations of the products go up during the course of the reaction, but they're going to be negative for reactants because we are losing reactants as a result of this reaction. So let's consider an example chemical reaction here where we've got 2 moles of A reacting with 1 mole of B, and they are producing 1 mole of C and 3 moles of D. And let's suppose that before the reaction here, we've got 1 of the A, 1 of the B, 0 C, and 0 D. After the reaction, what we do is we take our stoichiometric coefficients here, and we have our initial concentration, which is 1, minus then 2, our stoichiometric coefficient for A, times Kc. So as this reaction progresses, we've started off with 1, and then we're going to lose 2 times the extent of the reaction, because of the stoichiometric coefficient of 2. With B here, this stoichiometric coefficient is a -1 because we've got 1 mole of B that's a reactant, and because it's a reactant, it's negative, so we're losing that amount of the reactant. Therefore, as the reaction proceeds, we've got 1 minus Kc amount of B. Now with the products, these stoichiometric coefficients are coming in as positive numbers because we are producing them, and therefore we pick up Kc amount of C. And with the stoichiometric coefficient of 3 for the D species, we get 3 times Kc after the reaction. Now, the next topic here is the rate of reaction. The rate of the reaction is defined as shown here. So the rate is this capital R, and the rate is the time rate of change of the extent of reaction. So in this upper right-hand corner, we've got this general formula for how the number of moles of each species I is evolving. The little n sub I is equal to the initial amount plus the stoichiometric coefficient for that component I times the extent of the reaction. So this parameter here, Kc, the extent of the reaction, is really key to telling us how far along the reaction has proceeded. And so if we take the time rate of change of that, this d Kc dt, that gives us the rate of reaction here, R. So the rate of change of the number of moles of species I, therefore, can be written as, if we just take the time derivative of both sides of that equation in the upper right, then we've got the time derivative of the molar concentration of n sub I. The initial concentration here is a constant, so when we take the derivative of that, that goes away. And then we've got the stoichiometric coefficient, nu sub I, times the time rate of change of the extent of reaction, d Kc dt, which of course is just the rate here, R. And so we could take that R and put it in here for this d Kc dt, and that gives us the time rate of change of the moles of each species. Now, if the species are contained in a constant volume, it is common to write this in terms of concentrations rather than in terms of number of moles. The concentration of a species I, C sub I, can be written as the number of moles of that species per unit volume. So N sub I divided by V. And we can write this in equivalent notation then as in terms of concentrations as 1 over V times d Kc dt is equal to 1 over our stoichiometric coefficient, nu sub I, times the time rate of concentration of species I. And this is just using our definition here of concentration. The next topic is to determine the order of the chemical reactions. So most of chemical reaction kinetics is actually determined empirically by measuring the reaction rates in experiment and then using basically differential equations to fit the data that you get. And one of those fitting parameters that is commonly used is the order of the reaction. So when reaction rates are measured experimentally, they often follow, it's kind of shown experimentally, that they follow the equation shown here. So the 1 over V d Kc dt is equal to K here, some sort of rate parameter, times the concentration of one of your reactant species A raised to the alpha power times the concentration of B raised to the beta power. Or we can write these concentrations here using the square bracket notation as the concentration of A raised to the alpha power and times the concentration of B raised to the beta power. Now these exponents here, alpha and beta, are called the orders of the reaction. And the nomenclature that is used in chemical reaction kinetics is to say that it is of order alpha with respect to A and of order beta with respect to B. So you look at those exponents and say that the reaction is of order and then give the number of that exponent. For example, what if you have 2 moles of hydrogen iodide reacting to produce hydrogen gas and iodine gas? The rate equation for that is minus the change of the concentration of hydrogen iodide, and that is the derivative with respect to time, equals some kinetic coefficient times the concentration of the hydrogen iodide squared. And this would be of order 2, or of a second order reaction with respect to hydrogen iodide in that case. How do we determine the order of reactions? If we have a general equation like this, our task is to determine alpha, the order of the reaction with respect to A, from experimental data. The most convenient way to do that is to take the logarithm of both sides of the equation. So if you've got the logarithm of this rate here on the left, and then on the right, when you've got the K coefficient, times the concentration of A raised to the alpha power times the concentration of B raised to the beta power. The nice thing about logarithms is that that product then converts into a summation. So we've got the log of K plus then, and then the exponents come down in front when you take the logarithm. So it's log of K plus beta times the log of the concentration of B plus alpha times the log of the concentration of A. And depending upon how the concentrations of different species vary, then you can determine the alpha and or beta coefficients there. So for example, if the concentration of B does not change appreciably during the reaction, then the slope of the curve that you get would directly give you alpha. So taking the logarithm of both sides of the equation is convenient then to obtain the order of the reactions using your experimental data. Next topic is equilibrium constants of the reactions. So let's consider the reaction of a molecule that is dissociating to form two ions. So if we've got some compound here, MX, and let's suppose that dissociates to form at the M plus cation plus the X minus anion. The equilibrium constant for this reaction is the product of the concentrations of the reactants. So this would be the concentration of M times the concentration of X, and then divided by the concentration of the reactants. It's the product of the concentration of the products divided by the concentration of the reactant, and that gives you the equilibrium constant. So everything that's on the right-hand side, multiply those concentrations divided by the product of everything that is on the left-hand side of the equation. So if we consider the reaction of a molecule dissociating to form two ions, we can consider that there is a forward rate of reaction here, F plus. This is what is driving the reaction in the rightward direction. So this would be driving the dissociation of the MX compound to form the M plus cation and the X minus anion. At the same time, there's also a rate of the reverse reaction, F minus, and that's driving the reaction leftwards. So taking these ions and putting them together to form this compound MX. If we assume that we have a first order reaction kinetics here, then what we can do is write the overall rate equation following this master equation approach, where the change of the MX concentration with respect to time is then equal to, and with the forward rate of reaction here, we're losing concentration of MX, so there's a minus F plus, since this would lead to a decrease in the concentration of MX, and that is multiplied by our concentration of MX, and then plus F minus, because everything that goes in this reverse direction is going to give us a positive amount of MX. So we've got our plus F minus here for the reverse rate of reaction, and that's multiplied by the product of M plus and X minus. So you've got the term here that decreases the concentration of MX and the term that increases the concentration of MX. And if you add those up, then you get the total change of concentration. How do we get the equilibrium constant from this? At equilibrium, what we know is that the rate of change is 0. So to get the equilibrium constant, we take this differential equation and we set it equal to 0. And when we set this equal to 0, then we can take this one of these terms here and move it over to the other side of the equation. And what we see is that we have a balance of the rates here. So it's the F plus times the concentration of Mx is equal to the F minus times the product of the concentrations of M plus and X minus. Now the equilibrium constant here, K equilibrium, is equal to the ratio of this forward rate F plus to the backward rate F minus. So if we rearrange the equation here, dividing both sides by F minus and dividing both sides by Mx, we see that the equilibrium constant KEQ is equal to this ratio of F plus over F minus, and that is equal to in the numerator, the product of the concentrations of the products. So it's the concentration of M plus times X minus divided by the concentration of Mx. So that is where the equilibrium constant comes from. Just noting that when you achieve equilibrium, that the change of the concentration of the species is 0 at that point. So you set the differential equation equal to 0. So the ratio of forward to reverse reaction rates is the equilibrium constant, and that's how we get it in terms of this ratio of the various concentrations. Now, let's consider solving one of these reaction equations for a simple first-order reaction. An example of a first-order reaction is the decomposition of some material A into a product. We first treat the case where only the forward reaction is important. So, for example, this would just be a decomposition reaction where you have some amount of A here and it decomposes into products. Now, if we have a first-order reaction to represent this, we can describe this using the equation here in the lower right, where this is showing that the minus of the change of the A concentration with respect to time is equal to K times the concentration of A. So we're losing some amount of A there. This is why we have the minus sign. It's a first-order reaction, so that's why this concentration of A is raised to the first power. The rate parameter here is K, and this is proportional to the concentration of A, just because that is the only reactant that goes into this equation. Now, how do we solve this? If we consider that the initial concentration of A is A0, then what we need to do is integrate both sides of the differential equation. So we've divided both sides here by the concentration of A. So on the left-hand side, we've got the D times the concentration of A over A. And on the right-hand side, it's the minus K dt, where we've divided both sides by the concentration of A, multiplied both sides by dt. Now we've got the differential with respect to A on the left, the differential with respect to T on the right, and we need to integrate both sides of those equation. So on the time integral side, we're integrating from time t equals 0 to time t. And on the left-hand side, we are integrating from the initial concentration of A0 to the final concentration of A. And these are both standard integrals. And so what we have is the natural log of A divided by A0 on the left-hand side equals minus KT on the right-hand side of the equation. And if we solve for that, we solve for that by taking the exponential of both sides and multiplying by the concentration of A0. And this is how we get this simple exponential decay function. So the concentration of A is equal to the initial concentration of A times this exponential decay function e to the minus KT. So the solution to this very simple first order reaction equation for chemical reaction kinetics, considering just the decomposition of A, is this simple exponential decay function. A good example of this kind of reaction is the decay of a radioactive species. So for example, what if we have some initial concentration N0 of a radioactive species? Over time, the concentration of that species N is equal to N0 times our exponential decay, which is e to the minus lambda times t. And what we can do is take the natural log of both sides of the equation in order to linearize this. So you've got the natural log of n on the left-hand side equals the natural log of n0 minus lambda times t. And written in this way, we can see that this parameter here, lambda, is called the decay constant. The decay constant for radioactive decay is most commonly expressed in terms of the half-life of the species. The half-life is how long does it take for half of the concentration to decay. And that is typically represented by the parameter here, tau. And based on the definition then of the half-life occurs when the concentration of n over the concentration of n0 is equal to 1/2. Or in other words, when you have exactly 1/2 of the initial concentration of the species remaining. So we have n over n0 is equal to 1/2. We set this equal to our exponential decay function at the time equal to the half-life tau. So it's e to the minus lambda times tau, because we are at the specific time where the remaining concentration is 1/2 of the initial concentration. Now, we can solve for lambda in terms of tau by, and lambda is equal to the natural log of 2, because we got the 1/2 out in front here, divided by tau. Or in other words, we can change this exponential representation instead of being e to some power, so that it becomes 1/2 to some power. And using this half-life notation, then the n is equal to n0 times 1/2 to the power t over tau, where tau is the half-life. And so this is a mathematically equivalent way to describe that radioactive decay reaction. And this is the more common way to express radioactive decay, since it is expressing it in terms of a half-life tau. Okay, now let's consider first-order reactions with both forward and reverse rates. So we consider a first-order reaction in which both the forward and the reverse reactions must be considered. With radioactive decay, the reverse reaction is not happening at all. That rate is effectively 0, so we didn't have to consider it. But now let's suppose that we've got some reaction here between some reactant A and some product B, where we've got our forward rate of reaction F plus going from A to B, and our rate of the reverse reaction F minus going from B to A. So in this case, we can set up our rate equation as minus the change of the concentration of A with respect to time is equal to, and we've got our forward rate, this is losing A, minus our backward rate where we gain A. So the summation here tells us the change of the concentration of A. So what do we know at equilibrium? At equilibrium, the change of the concentrations is equal to 0, which means that F plus times the equilibrium concentration of A is equal to F minus times the equilibrium concentration of B. The equilibrium constant, KEQ, by definition, is this ratio of the forward and reverse reaction rates, which is F plus over F minus. We can see by dividing both sides of this equation by F minus and by A equilibrium that this is equal to the equilibrium concentration of the product B divided by the equilibrium concentration of the reactant A. So the equilibrium constant can be expressed either as this ratio of the forward to reverse reaction rates, or equivalently as the ratio of the equilibrium concentration of the products divided by the equilibrium concentration of reactants. And this is equal to e to the minus then Gibbs free energy that is associated with this reaction over the gas constant times temperature, or in other words, e to the minus difference in chemical potential between the product and the reactant phases divided by RT. Now, if we take this equation here and substitute it into our original kinetic equation from the previous slide, then we can express the F minus in terms of F plus and combine like terms, such that instead of having separate terms here for F minus and F plus, that we've represented this entire equation just in terms of F plus. Of course, you could do it the other way too and just express it in terms of F minus. Now, what if we have higher order reactions? The mathematical representation of the kinetics of higher order reactions is a straightforward exercise in calculus. Let us consider a second order reaction that has the differential equation shown here. So minus the time rate of change of the concentration of A is equal to some kinetic coefficient K times our concentration of A raised to the second power. So it's a second order reaction. So the exponent here is 2. There's a standard solution to this differential equation, which is 1 over the concentration of A minus 1 over the initial concentration of A is equal to KT. If you have a second order reaction with 2 reactants, let's suppose that you've got A plus B is equals some products. Then the reaction rate would be the time rate of change of A with respect to T is equal to minus K times the product of the concentrations of the reactants. So the concentration of A times the concentration of B. And likewise, this has a standard solution from for your differential equations class. So the logarithm of the concentration of A divided by the initial concentration of A minus the logarithm of the concentration of B divided by the initial concentration of B is equal to minus K, the difference between the initial concentrations of B and A multiplied by time T. We can keep going. So if you've got a third order reaction kinetics here with a cubed power in the kinetic equation, the solution in this case is 1 over the square of the concentration of A minus 1 over the square of the initial concentration of A is equal to KT. And so on. Next topic is to consider what if we have reactions in series. So this is if the entire reaction is not occurring in one step, but it is occurring in multiple steps in which there's at least one intermediate reaction that takes place. For example, consider the case of some material A that decomposes into a material B, which in turn forms a material C. So in this case, we have a reaction rate of going from A to B, which is F1, a reaction rate in going from B to C, which is F2, and then we've got an overall reaction rate F, which goes from A to C. But in order to get from A to C, we need to go through B. Now let's suppose that our initial concentrations of the species are that we've got a 0 amount of A and 0 of B and 0 of C. Then what we want to know is what are the concentrations of each of these species, A, B, and C, at any point in time during the reaction itself. Now, with these reactions in series, the overall rate of the reaction, in this case from A to C, is going to be governed by the relative rates of reaction F1 and F2. So how fast is it going from A to B versus how fast is it going from B to C? Whichever one is slower is going to be the rate limiting reaction. And so if you are a chemical engineer, what you would need to do if you want to accelerate the reaction is to come up with a way to accelerate that part of the reaction. So for simplicity, let's assume that the reactions are all first order. When we have that, we can set up 3 differential equations that describe the time rate of change of each of these species. So the minus the time rate of change of A is just equal to F1 times A, because however fast F1 is, that's the rate of loss of the concentration of A. Now for B, we've got a term here that increases the concentration of B, which is just our F1 times the concentration of A. So every time we lose some amount of A, we gain that amount of B. But we've got a negative term here because we are also undergoing the second part of the reaction with the rate F2. And as that reaction proceeds, we are losing B and we are creating C. And that's what also gives us this final differential equation, which is the time rate of change of the concentration of C is equal to F2 times the concentration of B. So we've got this kind of simple system of 3 coupled differential equations that describes the entire time evolution of this process. And if we integrate all of those differential equations, the first equation is the simplest. This is just the exponential decay function. So the concentration of A is equal to the initial concentration of A times the exponential decay e to the minus F1 times T. Now, what we need to do is take this equation and stick it into the differential equation for B. And when we do that, we can solve for the concentration of B. And you'll note that this is in terms of the initial concentration of A, and then the two reaction rates, the F1 and the F2. And then you've got a product of a couple of different exponentials here. This then is the equation for the concentration of B, and that gets inserted into the differential equation for C, thus enabling us to solve that. And then we get the final form of the concentration of C here, which you can see depends on the initial concentration of our first reactant, A0, and then some ratios here of the reaction rates of F2 and F1. And qualitatively here, the thing to note is that the reaction from A to C, the overall reaction rate, is controlled by whichever is the slowest rate in the series. This is known as the bottleneck principle in chemical reaction kinetics. So if you want to accelerate an overall reaction rate, if you're, say, producing some chemical, you need to identify which is the slowest part of that reaction. That is the bottleneck, and then do something to accelerate that part of the reaction. Okay, now let's consider the temperature dependence of the reaction rate. This original work was done by Arrhenius a long time ago, who observed that the rate of the change of the equilibrium constants with temperature could be expressed with this equation here. So that this is the how does the reaction rate of some chemical reaction change with temperature? And what Arrhenius observed experimentally is that it's given by some sort of activation barrier here, delta H, divided by the gas constant times temperature squared. And by extension, then, if you use this differential equation for the temperature change of the reaction rate, so the dF plus, the forward rate of reaction with respect to temperature, is equal to some E star. That would be the activation barrier for that forward reaction divided by RT squared. So if we take this equation now and multiply by our dt here, we can have the d of f0 is equal to this equation here on the right-hand side, and integrating both sides of the equation then immediately gives us this exponential. And if we take the natural log of both sides, that linearizes this reaction rate with respect to 1 over the temperature. And you can see that this is another way of obtaining the Arrhenius equation. Remember back in chapter 7, we obtained the Arrhenius equation based on the underlying statistical mechanics. But what this is telling us is that the reaction rates are increasing exponentially with increasing temperature. All right, next up is heterogeneous reactions. Most studies in chemical reaction kinetics are concerned with chemical reaction rates in homogeneous chemical reactions. In other words, where the reactions are occurring within a single fluid phase. However, many reactions of interest to material scientists are heterogeneous. These are reactants where you have reactants present in different phases, or where the reactions are happening at a phase boundary. And these heterogeneous reactions typically take place by a series of consecutive steps. For example, what if we consider a simple reaction of a gas dissolving in a metal, for example, hydrogen dissolving in aluminum? This reaction takes place over a series of steps. First, there is the transport of hydrogen molecules by diffusion or convection in the gas phase to the gas-metal phase boundary. Next, the adsorption of hydrogen molecules on the surface of the aluminum. Step 3 would be the decomposition of the adsorbed molecules into adsorbed hydrogen atoms. 4 is the solution of adsorbed hydrogen atoms into the aluminum at the gas-metal phase boundary. Next is the transport of the dissolved hydrogen atoms away from the phase boundary. And again, as with the reaction series, since the heterogeneous reactions take place in steps, a question becomes, what is the rate limiting step or the bottleneck in this heterogeneous reaction process? So in principle, all of these steps can be regarded as limiting the rate of the overall reactions, acting as like resistances in series, if we were to take an electrical engineering analogy. In practice, though, it's usually one step that is the slowest one, the bottleneck, that effectively determines the overall rate of reaction. Because each of these consecutive reactions has its own activation energy and hence its own temperature dependence, this rate limiting step may vary as the temperature is varied. So just because something is the rate limiting step at one particular temperature doesn't mean it's the rate limiting step at all temperatures. All right, the last topic for today deals with solid state transformation kinetics. Many of the reactions of interest to material scientists involve transformations in the solid state, such as, for example, recrystallization of a cold work material, precipitation of a crystalline polymer from a non-crystalline phase, or growth of an equilibrium phase from a non-equilibrium structure. All of these could be examples of solid state transformation kinetics. So let's consider some phase reaction, where we've got some phase here, alpha, that's being transformed into a different phase, beta. So alpha is going to beta, and let's take the total volume of the sample, V, as equal to the volume of phase alpha, V alpha, plus the volume of phase beta, V beta. We can write the fraction of the transformation as simply here F. So F is the fraction of the system that has been transformed into the new phase. That is simply the volume of that new phase beta divided by the total volume of the system B. And let's assume that the process of phase transformation is governed by first a nucleation process and then a growth process, as we did in our chapter on nucleation. So if we have nucleation and growth of a new phase, we can define this N dot here as the nucleation rate per unit volume, and the G dot is the growth rate of that new phase in one direction. So that's equal to dr dt, where r is the radius of that new phase. And if it is nucleation followed by growth, the key is that nucleation has to happen first. Once a stable nucleus forms, then it can grow. So if we look at this as a function of time, t, nucleation takes place up to some certain time that's labeled as tau. And then we measure some new time after the stable nucleus is formed. That's where it grows, and that would be at all of our time after tau. So let's consider now the number of nuclei that form during the time d tau. The number of nuclei that form would be the nucleation rate here, N dot, times the volume of our initial phase here, V alpha, times the amount of time that has elapsed during nucleation, which is labeled here as d tau. So the product of all of these terms would give us the number of nuclei that formed during that time, d tau. Now, assuming that the nucleated particles grow as spheres, the radius of the particles then is simply we integrate the dr from 0 to r, and this would be integrating our rate here, g dot, from tau, from this time where the nucleus forms, to some new rate t, in this, or to some new time t integrated over tau. And if we integrate both sides of this equation, what we get is r on the left-hand side, and then g dot times t minus tau. So the growth rate times the time that has elapsed since the stable nucleus is formed, which is t minus tau. So this time gives us how much time has elapsed since the stable nucleus is formed. That is how much time is available for growth. And the G star is the growth rate expressed in linear dimensions. And then that would give us R, which is the size of the nucleated new phase. Now, the volume of the nucleated particles here, if we've got dV beta, so this is the change of the volume of the new phase beta, this, using the equation for the volume of the sphere, since we are assuming it's spherical, is 4/3 pi, and then this equation cubed. So it is the crystal growth rate cubed times the time that has elapsed cubed. and then multiplied by n dot, which is our nucleation rate, and the volume of the initial phase alpha times the d tau. This is taking our total number of nuclei that are formed from the previous equation here. Now, what we need to do is we've got the dv beta and the d tau on this side. So let's simplify the right-hand side of the equation as shown here, where we can write the v alpha in terms of v beta. The v alpha is just v minus v beta. Now, we are prepared to integrate both sides of the equation. So we're going to integrate the v beta from 0 to v beta. So this is integrating from initially 0 amount of the new phase beta up to v beta amount of that phase, integrating the right side over the time from time equals 0 to time equals t. And when we do that integration, we have that the v beta is equal to v times pi over 3 times the g dot cubed times n dot times t to the 4th power. And this is the Johnson-Mehl-Avrami equation. This tells us how the volumetric fraction of the new phase beta, how that is growing over time, given some nucleation rate n dot and some growth rate g dot. And so this is actually a really nice derivation of the Johnson-Mehl-Avrami equation in the context of solid-state transformation kinetics. This is the same equation that we already saw in the chapter on nucleation and crystal growth kinetics. So to summarize, we have considered homogeneous and heterogeneous reactions, as well as solid-state reactions. Reactions can be first order or higher order, where the reaction rate is typically found through experimental measurements. For reactions in series, there's typically a rate limiting step. And we've shown how you can derive the Johnson-Mehl-Avrami equation for growth based on reaction kinetics. So thank you very much for listening. If you have any questions, please let me know.